a Toronto model with some kind
Yeah,
of
let the guy
real big
respond,
gaseous
brother.
plasma.
Let the
But,
brother respond. I'm just tuning in,
okay.
but yeah. What's up, Professor? Professor.
Two things. If you take a bowling ball, sit in a wheeled chair, and you throw that ball away from you, do you think that you're moving backwards because the bowling ball is pressing against the air? Second
Yeah, but
thing is,
it's a false.
no, you
It's a
don't
false.
lose the weight.
That's a false.
Not
That's a
analogous.
false. Yeah, it's not analogous though.
It's entirely analogous. If you take a rocket, essentially it's throwing matter out the back as you burn it as exhaust, throwing it out one end while you go the other way. That's exactly the same.
Have you ever seen a clock in a vacuum, bro?
Well, hold on.
It
The
doesn't do
mechanics of
anything.
your. Well, no,
Yeah.
the mechanics of
And
throwing the bowling ball.
wheelchair is on the ground to begin with. It's already
One at
against
a
something
time.
solid, the
That's
wheelchair.
what I'm saying. Is
Go ahead.
that's what you'd expect.
What were you
What?
gonna say, Issa?
Well, no, I was gonna say like when you pull up, if you like pick up a bowling ball and you're gonna throw it, like it's your elbows have to get out of the way. Like you're making this like you kind of lean back almost as you generate the force to push the bowling ball. Like that's completely different than like lighting something on fire, creating energy, and then pushing off of. Like there's nothing to push off of. Like it's just not analogous. That's a great way to say it. And from my understanding, how do you think it's analogous?
I bet I'm not answering that question. I'm just throwing a thought out there. I bet if you had a vacuum that was big enough and you were in a wheelchair in a room with regular normal 14.7 and threw the bowling ball and then did it inside of the vacuum environment with as low as pressure as you could possibly get, I bet that you'll have less of a travel distance in the vacuum than you will inside the 14.
No. Because that force is generated off your heels, pushing off the ground. Like, you know what I mean? There's like all this other force energy. It's just not analogous. And I was going to ask you, why do you think that isn't, why is that analogous to you?
Why would your feet be touching the ground?
Well, I'm not going to pick up.
Sit cross-legged.
All right, how about this? My hips, like everything is generated, like the force that's being generated is not, you can't liken that kind of a generation of force to like the explosion of, like it's likening like me throwing a bowling ball to like firing a gun. You know what I mean? It's like there's nothing. First off, a gun's not going to work without something for the thing to push out through. Like you have no means that the combustion could push anything. It's just like, I mean, Beasticle said it best. It's just not analogous. Why do you think it's analogous?
The fuel
gun would
source is within the combustion.
Hold on, let him answer though. What is it, brother? Why is it analogous?
I don't understand why you think it isn't. Just because the particles being chucked out as exhaust are smaller than the bowling ball. And incidentally, if you were to fire a gun, we're not talking about there simply being a vacuum. A vacuum doesn't sort of affect the gravitation in any way. So if you're, on a, well, let me see. If you're sitting on a chair and in a vacuum, which seems a bit strange thing to want to do, and you were to fire a heavy gauge gun, there would be recoil still. You would still fall backwards. That's simply what you would do.
Yeah, but that's only because it's pushing off the back of the gun. It's pushing off the back of the gun to create the recoil.
Well, yeah. Well, if you replace the back of the gun with a rocket, that is what it's pushing against. Exactly.
Yeah, but there's no wall. Hold on, there's no wall for the back of the rim to shoot off of. But who's trying to chime in?
Issa, I'm just trying to get in here for one moment. I'll just give you a quick angle on this, right? So it's all about dynamics as far as I'm trying to get my head around as far as this topic. The professor is referring to the notion that if you have a mass and you split that mass in half and you push away one mass from the other, this you could cause what we might say is an acceleration, right? But these are crystalline structures. Solids are crystalline structures, and you're using that mass to push off from the other mass. What's being used in rocketry is fluids. It's fluid pushing off fluid, and it's actually fluid pushing what a mass, a solid object at this point. The fluid dynamics are completely different to the crystalline structure of a solid. This is like the primary issue as far as the thought that you can use a rocket exhaust as a propulsion method within a you've got no other fluid to push back against. Thus, it's causing a big dilemma as far as the dynamics of how this would actually work in a vacuum. Do you get where I'm coming from, Professor?
Yeah, I've heard people say this, and it doesn't make sense to me. To every action, there's an equal and opposite reaction. And that doesn't matter whether you're in a vacuum or not. That law is a law, it applies. So if you throw something out the back, you go in the opposite direction. It is being pushed out the back at speed. You then accelerate the other way, just the same way as you would do if you threw a bowling ball. It doesn't matter that the bowling ball is solider. The individual particles are smaller, sure, there's just a lot more of them. That's all.
Do you recognize that in space, as soon as that fluid exits out the injector, the dynamics of space is wanting to pull? People say there isn't a pulling force. It's wanting to fill up that, find its equilibrium. You can't generate a force to create propulsion on your rocket until you've overcome the equilibrium and then added a little bit extra. It's like you overcome the equilibrium, then you need to. But then, I'll land it there. I know where they kind of go with this discussion, but I'll let it play out. Do you get where I'm coming from, Professor?
I've heard what you've said. If you direct a stream of matter, eventually it's going to spread out. I mean, you can actually see this happening. If you launch a rocket, you'll notice that when it's quite close to the ground, the column of fire that you see is fairly narrow. As you go further up, it spreads out because there's less pressure to push against. And there's less pressure to resist it, to push it against itself in order to
It's moving through water too. Remember that. It's moving through a fluid down here.
So the question I got for you, does it become more efficient or less efficient at that point? Noticing that it's now spreading, right? Would you say that that's less efficient or more efficient as you go up?
It should become more efficient.
But you just said that the spout widens. If the spout is widening, it can't be directing the force through the vector, through the core axis of the rocket, because it's spreading it out and it wastes energy as soon as it starts going laterally, right?
Yeah, well, the point at which it is being ejected, after that, we don't care what's happening to it. Once it leaves your rocket, the instant it's done that, it's done its job, it's been thrown out the back. Whether it then spreads out is just not important. It's directed at the point of the mission, and that's all there is to it. I mean, that's
sorry,
why
keep pausing.
All right,
so there's a problem with that, right? Because when you have a rocket in a vacuum and you eject something out of the rocket, it goes in all directions of the vacuum, even in front of the rocket. Have you ever seen that, Professor? You ever seen a rocket inside of a vacuum and what happens? All the stuff that it eats. Okay.
I've never seen a rocket in a large enough chamber to be able to achieve what it is that it would need to achieve in a much, much, much larger one.
Yeah, but it has no thrust until it fills up the vacuum chamber.
It's really interesting.
Right.
They have that giant, that giant vacuum chamber that they have where they drop the bowling ball and the feather in one. I don't understand why they haven't just put a rocket down in there and activated that vacuum and put it down. So I believe they said they can get that chamber, that entire 3-story vacuum chamber down to 3 grams of air, something like that. And then, so yeah, you would think they would just, shut everybody up and throw a vacuum, a little small,
it takes
model
3
vacuum in that
days.
joint.
It takes 3
3
days to
days
pull
to
that
get
vacuum,
down to
by the
that
way.
3 grams. 3 days to get to 3 grams.
Constantly pulling. Yep.
That 3.3,
Yep.
love it, man. Gotta love it.
And the issue
Pumping
is
air
as
out
soon as you turn
constantly
that
for
rocket
3
on,
days to get it down to max.
That's wild.
as
But
soon
yeah,
as
you would
turn
think
that
they just
rocket
put a
on,
little small model
you've got
rocket in
pressure.
there. Sorry, Rick, I didn't mean to cut you off. Go ahead.
Yeah, bro. I just say that as soon as you turn that rocket on, it's going to be expelling your vacuums going down or up, whichever way you want to refer to it. As soon as you turn that rocket on, the pressure is going to start going up. So you got a moment's time to test it right at the start, where you're in true vacuum before the exhaust starts filling up the space and creating the pressure again.
Well, I mean, this is like a 3-story vacuum chamber, and I think we could make like a small model rocket, kind of
I
just
like
a
that idea.
small
Yeah, that's
scaled
what I'm
down,
thinking. Yeah,
just to see if you can even get a
'cause
lift
I'm
off. You
thinking,
know what I mean?
yeah, and I'm thinking it would crush that thing. If it takes 3 days to suck all the air out, they would have to make that rocket pretty solid and thick, you would think, to get any kind of lift, even if it would lift.
I think it
That's
would
what I'm
lift. I think it would lift, but it would be such a chaotic lift that it would flip it, because like it would just flip the thing over, because it would try to equalize so fast that all the propellant or whatever would just the second that you open that pressurized source,
Yep.
without that barrier to that huge vacuum, it's going to equalize, and it's going to do it rapidly. So I think it would all just expel ridiculously fast, and then you would just see maybe one like the thing would just kind of jump up in the air and flip over on its side, and that'd be all of it. Just be like a puff of vapor.
Well, I think it works the same way, right? They use aerodynamics.
To try to stabilize it, yeah, probably. I mean,
There's no aero for the aerodynamics to function, is there? That's the point.
Exactly. Yeah.
There you go,
problem
Professor.
is-
You got it now.
Yeah. The problem is they claim these specialized nozzles, and they can angle the nozzle, and then have like some other type of chamber at the end of the rocket to basically focus the release of it, etc. But in a vacuum, especially in a huge vacuum such as the vacuum of space, a nearly perfect vacuum, all of that would go everywhere at once, including towards the front of the rocket. No matter how much you angle it, it's going to fill the vastness of space, right? It's going to fill that empty space. So you'd have to be wasting so much fuel. That doesn't make any sense.
The thrust is aiming it one direction, though.
Yeah, but it doesn't go in
But you
one
can't
direction.
you can't have thrust without the matter to thrust off of. That's the whole point.
Right. It'll just leak out into the empty vastness of space.
yeah, and I think also, Professor, a good point is maybe you're picturing those, launches, they say come down back into the atmosphere and shoot up a thin jet. I think that's maybe you're conflating that with no pressure at all in a vacuum versus the gases down here.
Not at all. I've never even seen one of those until very recently. All I am saying is that the usual law of equal and opposite reaction means that if you throw your energy out one way, and incidentally, there's no reason for it to sort of like go anywhere other than the direction it needs to go. You're giving it thrust in a particular direction. It might expand, but it'll still continue going in that direction.
Yeah, but that was derived. That was derived here on Earth, though.
I put a video of a small scale test in a vacuum, and it does fly before the container is filled.
Let's see. What was I going to say about what you professor just said?
Hold on, wait, where?
Damn, go ahead, guys.
Live stream one text.
I see it.
It's a small one, but I'd imagine it worked the same way. As long as there's a pointed thrust system in the back, it's going to go forward.
Oh yeah, hey, this is what I was going to say. I'm still on subject, but you remember, Professor, back when they did that SpaceX launched there was like an X-90 some odd jet, like a outer space prototype, and where they shot it up, and they were supposed to go, so fast and so high that they launched it from a plane first, like, way, way, way up, and then it was recorded and went up to 200 and something thousand feet, and it was live, and you could see when this thing just started spinning out of control and going around, And they kept saying, oh, 260, oh, 300,000. You could clearly see that it was like floating and spinning, like almost like it was just dropping back to the earth. It just ran out of atmosphere.
Oh, I know nothing
It
about
couldn't
that.
push no more.
Oh, wait a
I just
second.
shared the video. There's a
Yeah.
video in the chat.
You
And
remember
it
that?
doesn't move. Rocket doesn't move until the thrust part. You can
Hits
see
the
smoke
wall.
come out until it hits the
Yeah.
wall and pushes off the wall. It doesn't go anywhere until it hits the freaking wall.
Yep. Yeah, it literally doesn't move until it hits the wall, Anchovy.
And even though like people get mocked for it, that's kind of what the idea of the sucking of the vacuum force is, right? Because the environment of space is so large compared to the small pressurized tanks.
Yeah, exactly.
So
Dude. Doesn't make any
the
sense.
moment, yeah, the moment that that tiny tank opens that valve ever so slightly, that huge environment, it's going to go try to equalize into there, and it's going to do it so rapidly.
And you're not going to move at all.
Exactly. It's gonna just pull whatever's in there right out.
Yep.
And imagine the scale, right, of what we were calling the universe when we look up. Dude, this on scale to a rocket, no matter how big it looks down here compared to the sky. I mean, yeah, you know what I mean. It would be cartoonified, like, choom, like all the gas going. Choom.
Yeah. So, Anchovy, do you have anything to say about that? No. Take your silence as concession, then. Yeah. So
You had me at hello. Oh.
there's no thrust being able to be achieved in a vacuum-like environment. That's the problem.
Hey, Professor, if you come over to this side and we just team up, we'll be stronger and we can figure this junk out faster.
You know, I have no doubt if it wanted an actual vacuum and it didn't have anything to push off of, that it would probably, it might do some kind of weird freaking movement, but it's not going to be, it's not going to be anything. It's not going to have anything to push off of. Just maybe from the chemical reaction or whatever kind of reaction you're using, push it. There might be some movement, but I just don't. It's not going to be any thrust happening.
Now, if you get up higher, Professor, and you catch that toroidal twist, that fluid or gaseous plasma that hadn't been ionized yet, the ether background, whatever you want to call it. I mean, yeah, possibly. I can't deny that.
I really don't know anything about that either. I'm a historian, not a physicist. But as I understand it, the second law should apply. And I'd be very surprised to find that it didn't. But I looked at your little rocket thing, and I noticed that it began to, first of all, it's going to start to accelerate. It actually has to overcome inertia first. So you'd expect it to take a little while to get going. But that also is what you would expect. You'd expect it to take a little while to get going. And, because it has to overcome that, build up enough thrust to be able to overcome that, and then start it moving, and then it should begin to accelerate relatively rapidly. But
you saw why, though, right, Professor?
It's
because it hit the wall.
Exactly why. I don't think it's because it hit the wall at all. The chamber was too small to prove it.
Bro, it doesn't move until the stream hits the wall. You can literally watch it. I'll repost it.
What a stream of gas hitting a wall n lengths away.
And now it's pushing off the wall.
Has to do with it moving is something which I don't see at all. What those molecules are doing when they touch the wall isn't having any impact on what your rocket is doing, so like 5 rocket lengths away, is it?
Incorrect.
Well, okay. I guess we'll agree to differ there. Okay.
I mean, dude, you can literally watch it. It doesn't move at all until the stream hits the back of the wall. Now it has something to thrust off of. Now it moves. So that means in a vacuum, if it was just floating in space and it was just pushing shit out the back of it, it would not move. has nothing to push off of. The only reason why it started to move was because it hit the wall. Now it has something to push off of. It's very simple.
Right. On the one hand, I understand why you are saying that, and on the other hand, I know that end rocket length away from it, the fact that some molecules happen to have touched the wall is having no effect on the rest of the column and having no effect on the rocket. So
how do you know that?
Because there's no way in which it could. It's
you
a matter
can
of
literally see
dynamics.
it
No,
pick
you
up
can't.
thrust. It hits the corner. I just posted it again for you.
Yeah, I've looked at it. Thank you. I've seen it before.
Okay. Well, so it's not moving at all when it's thrusting out the back. Now it starts to move when it hits the corner. It has stuff to push off of. I mean, you can close your eyes and say, but dude,
I
it's
don't
not
need
working.
to say, I can see that the molecules touching the wall are having no impact upon the rocket because there's no connection between them in order for that to happen. Is there? As if it was a rod or something, an actual rod that kind of prodded into something and pushed off it, that would work perfectly fine, and I'd understand that. But there is no connection between the two.
That's fine, bro. You can believe whatever you want to believe. Put your head in the sand, dog.
I can see that there isn't a connection between them because it's basically just gas in a chamber, which incidentally is also dissipating. Look, it's 4 a.m. here, okay? And I don't especially want to take a run right now. I'll stick around for a bit, but I'm going to have to go soon.
I have an idea, Professor, for you maybe before you go. It's a little off of what we were just talking about, but do you know what an omnidirectional treadmill is?
No.
Do you know what the omnidirectional eyes you look out of?
I'm sorry, I don't know what
like you can stand still but move your eyes and change your center of mass, center of vision.
No, I can change my center of vision by focusing somewhere
Not
else.
by walking, just moving your eyes or tilting your head or looking left or right, and you have a new center of vision.
Yes, that's understandable.
Right.
Yes.
I think this is how the whole world and light, I'm starting to think if it is a damn simulation, that we're just walking on an omnidirectional treadmill looking up, down, left, right, and we got headphones on, or AI, artificial intelligence kind of VR kind of headsets. Do you think maybe that's the way it is? The world isn't flat or round or celestial. It's just a celestial sphere you're looking at because your eyes are around you. Have you ever thought that?
Doubt very much that it would particularly
all your geography
with the shape of your eyes.
Let him respond.
Yeah. The notion that you could be on some sort of omnidirectional thing is what you're describing is very similar to this. I mean, I don't know if you've watched Star Trek at all. I expect you have. You must have heard of the holodeck. Well, you're in it somewhere. It's moving around you. You're tractioning against the floor as far as you're concerned. But in reality, you're only staying in a room, that's only so big. And everything around you is basically an illusion, projection, and a certain amount of physical objects to interact with. Now, if that were the case, that would be somewhat disappointing in many respects. There'd be no way in which we could tell directly that were the case, I think. And it doesn't add anything particularly meaningful or helpful to the discussion by saying, well, what if none of it's essentially real? Yeah, okay, that's always a possibility. But what we've got is what we can see and what we can interact with. And
yeah, just real in a different manner is what I mean.
We do that. Yeah, we do that. We deal with what we can see and what we can interact with, and if it turns out to all be an illusion, well, I guess the joke was on us, and it was nice that we at least thought it might be. But at the end of the day, I I'll sit down on my chair and it sort of feels comfortable when I do, and it's there and it's supporting my weight, and at least it seems to be. I react to it as if it were, and deal with the reality of myself sitting down, same as you do, same as any of us do. I suspect that the notion, that might just be some sort of force field creating the illusion of me sitting, isn't something that gives any sort of meaningful difference in the world, if you see what I mean. But I have heard that before. It's like these people who say, well, what if none of it's real? Yeah, it might not be real, but when you get hit by the bus, that's the last thing you're not going to be thinking is, wow, that bus didn't feel real. An illusion. It's just an illusion of a bus. You'll be thinking how great that hurt, and you'll be, doing whatever it is that happens when you get hit by a bus, whether you believe it's real or not. I suspect that the last.
Yeah, that's a good way to look at it.
Real.
Yeah, I like the way you put that, because if we only have 5 senses to deduce what's all around us at all times, like our environment, would it just make sense to buffer everything? Because everywhere you look and you move your eyes up, down, left, or right, it curves back on the edges, right, like your eye. And I'm thinking, if this was still real but in a different way, that maybe we don't have to travel all that far we just move our eyes left and right, up and down, and everything's rendering down to us, to our little bitty eyes in the center of the black hole, right? What our eye is about, in theory. I don't necessarily believe it, but if it kind of sucks that we only have 5 senses to deduce all this, in a short amount of time, and we're trying to figure it out and give it explanations, like all that pressure and stress, dude. The reason I ask you this is because when I finally woke up to what science was lying about, and I tried to figure it out for myself, and I'm like, okay, if all this is really not that far away, it just feels like it is, or you know what I mean? Like looking up in the sky and trying to figure out what's on the ground. It just gets complicated and overwhelming sometimes. So maybe I just want to pretend like sometimes I'm wearing a headset, and when I move my eyes, I don't have to move my body so much. I'm changing realities real quick. Anyway, man. Anyway.
That seems an interesting way of looking at things, and if it gives you some comfort, that's all the better for you. I wish I had something that gave me comfort like that, and there are times when I could really use it, same as any of us, I guess. If you take a light source, like a disco ball, for example, and you have it sort of like throwing light out so that it creates spots on a wall, okay? And you rotate that. By looking at the way in which the light moves, the shape that it makes against the wall surface, against the floor, against the ceiling, and so forth, the more data that you have about what shape those things are, and you should be able to map out quite well the exact dimensions and shape of your room that you're in. Not because you're just looking at lights and they're pretty and moving, but the way in which they interact with the area around it. No one ever said, looking at the stars, just tells you what shape the world is. It's how they behave in relation to the physical thing that the world is that gives you some idea as to what might be going on.
Can you dive a little bit deeper into that before you go?
The most obvious
example
of that then is if you take some a point and rotate some lights around it, your perspective of it is such that you're looking straight at the middle of it. They're all rotating in nice circles around that. If you move a significant distance away, it appears to drop in the sky. That's absolutely true. However, what you would expect to find is that the circles will become more elliptical.
Hey, Professor, if I look down with my eyes though, and that ball, that I don't look at the center anymore. If I look down at the floor, then that equally looks like the disco ball moved up. You know?
If you're talking about a fixed position, then that's fine. That's what I'm talking about. We're looking at them in a particular place. We're moving away from it while still looking in the same orientation. That's what you would expect to see. It doesn't. And that's fine. If you did it and projected it onto a curved surface, it would behave one way. It would behave radically different if you tried to project it onto a flat surface. Now, as you move away, you expect that to happen. It doesn't. What happens is that you maintain the relationship as if you're looking directly at the center of it, and everything is circular around it. And this is one of the things that led the Greeks in the first place to think, hold on, wait a minute. If we move further north or south, it doesn't behave the way we expect it to if the surface we're on is simply flat, because things should become more elliptical, they're not. And they considered that the situation that you would find is if you were on a hill or something, that's the effect that you'd have. Is that because the surface that you're on is tilted, the light coming at you can still sort of maintain that relationship. So it's not the fact that the lights are there and that it's the relationship between us and them. What was anticipated against what really happened. And it's not the only thing by any means, but generally speaking, it's the relationship that's happening, what it's doing in relation to us, that is different to what you'd expect if we were simply moving away from it in a planar way. One of those relationships, for example, is that over a significant distance, as it drops about 1 degree in the sky, you'll have moved a certain distance along the ground. Fine, no problem. For 2 degrees, it won't be twice that, it'll be a little bit more. And for 3 degrees, a bit more, and so forth, until you're looking at some quite significantly long distances in between each degree drop. That's what you would expect on a flat plane. Because you know how trigonometry works. You can draw the triangles out, and the star's not moving just because you are. It's still in the same place. If you are on a curved surface,
if you can't get off the surface to do the test, how can you differentiate that it's the Earth being round or flat?
Why would you need to get off the surface to show that?
Different reference frame.
You're moving along the ground. Okay. That's your reference frame. You're moving along the ground. And if the ground is flat relative to the object that you're looking at, then the distances that you have to move should increase over, the more degrees down it goes, the longer the distance you have to move to make it go down another degree. On a curved surface, that relationship is not quite so.
But either way, we have both because our eye is curved, right? We're dealing with 2 curved surfaces, or one flat and one curved.
We get the shape of your eye. Use a telescope or something. You are looking at something going down by 1 degree. That's the thing. You're measuring that. You're not just eyeballing it and thinking it looks as if it's a bit lower. Using, I don't know, something like a sextant to actually determine that it has moved, or at least.
Well, what I'm saying is your eye curves backwards on both sides, and just if you'll take 1 second and look and focus on one spot in the room or wherever you are, notice that you're focused in on that, right? Your pupil's dialed in on it.
Okay.
Now, to the left and right, I can't see past a certain spot, but I can see a peripheral, right, of, let's see, 180 degrees, right? Now, what I'm trying to say, I guess, what I'm trying to prove is that do the same tests 3, 4, 5 times, whatever, if it repeats, that's good. But that's only because your eye sees it in a curve, right? There's looking straight forward, that's a 90 or a zenith, and then left and right, there's 2 90 degrees. Your left side and your right side, right? So you see where I'm going with it? Like it only matters. The results matter about the shape of your eye. You have to count that in.
I don't think so, because we're not talking about periphery. We're talking about looking at a specific point.
No, your brain, how you interpret it is your eye. It's a sense to tell you about your environment.
You're looking straight at it, or you're not, aren't you? It's either the thing that you are focused on, or it isn't. And the thing you're focused on is the middle of your cone of vision, right in front of you, and your instrumentation is telling you, not just your eye, but the instrument, like a sextant, is telling you that seems to have dropped by 1 degree. And you can see it looking at it. I mean, once you've moved a significant distance away and it's dropped a few degrees, it's obvious. You look at it and it's not above you anymore. The point being that as you move the same distance over the surface, you're getting that same angular drop. Now, what I'm not telling you is I think this proves the world is a globe. Don't get that impression, okay? What I'm telling you is that the Greeks attempted to make sense of that by suggesting that that behaves consistently with the way you would expect it to do if you were standing on a curved surface. Because if you were, that relationship actually works, and it just works out of the box. That's exactly what you would expect to see. That's not to say that they are going to say it's impossible that it could happen on a flat surface, although it's difficult to see exactly how it could happen on a flat surface. It behaves in a way that's consistent with it being a curved surface. In science, you don't get proof. You get proof is for maths, alcoholics, and bakers. In science, the best you ever get is behaves consistently.
You said bakers?
Bakers, yes. Good. You proof bread, yeah. The thing about science is that the best you ever get is it behaves consistently with. And occasionally, if you're lucky, it can't be that because. And, that's what happens. And the problem with the globe, as I see it, is that it's difficult to simply say you can prove that it is, because as I've said, proof doesn't really belong to science. What you end up with is a series of predictions based upon its shape and its size as understood, and that will give you some predictions in the real world, which you can then go away and test and see if they're consistent or not. And just out of the box, you expect it to work in a certain sort of way. Now, we realize that light doesn't always travel in straight lines. You can cause light to bend. We've got a good idea as to what sort of thing causes that to happen, because in a lab you can go away and test it and find out what those conditions are. Do those conditions exist within the atmosphere? Yes, so that's going to change very slightly what it is that you should expect to see, because it's not out of the box anymore. It's had to be refined slightly because we actually have an atmosphere, which is a pain in the arse, but there it is. And it still behaves consistently. So, yeah, it's not what the lights are doing so much as the way in which they relate to what we are doing. That is why it is that the Greeks, at any rate, considered that might be the case. And they already had a kind of philosophical bent that it could be anyway, which just muddies things. But they did at least go out and try and find evidence for it. And that was one of the things that they noticed. As you go further and further north or further south, the path of the stars through the sky remains circular, and the distance that you have to move is consistent and constant. They concluded that geometrically this just doesn't work across a flat plane, whether it's 2 flat planes that are parallel or a flat plane and a curved plane above it. And neither of them fit that pattern. The only pattern that they felt it did if the surface was curved. And they thought this was an absolutely crazy idea, just the same as you do.
Like, what about the curve of your eye, though? You keep forgetting about that. Like when they take measurements, looking left or right, up and down, they got to follow that star, right?
No. You look straight
but your
at
eye
it.
has to follow the. Right, I get that, but you're looking at it straight on while it's moving, and if you keep looking at the center and you keep that star in the center of your eye, as it moves, you have to follow it downward with your eye.
Star isn't moving fast enough for you to be able to follow it moving. You know that. You can't watch stars moving across the sky in real time.
No. When you do a 24-hour or like in wherever, like a 24-hour night in Alaska, you will notice that they are consistent as they go around, and you're just really, you can follow it with the camera centered on it or your eye lens itself.
You can do that anywhere, can't you? It's not just at the poles that happens.
That's the point. That's the whole point, though. It could work on a flat plane or a globe. Your eye is going to be following those moving lights in the sky.
We're not talking about an eye, though. The only thing that's able to follow it is something with a really long exposure, like a camera. So you set up a camera to take a photograph.
Right. That's what I mean. That's what I mean. Yeah.
Pointing at the same spot, right in the middle. It hasn't moved. It hasn't changed its focus.
No, not the camera, but the stars. Right.
They seem to have rotated all the way around it in a circle, which, if you were able to do that with your eye, would be exactly the same. So the fact that it's
your eye can only see so far. There's a convergence point, right? In the distance where it disappears at.
Doesn't matter, does it? We're talking about
it's about your eye. Because if it disappears and then you take that zoom camera and you zoom in, you can bring it back into focus. It's not gone, but your eye can only see so far.
Yeah, but you're not conflating anything. You're just talking about two different things. I'm talking about looking at a single point and seeing that other things are rotating around that point, and that's something that has got nothing to do with your eye. Because you can confirm that it's doing that by virtue of the fact that if you point a camera at it, the camera shows you exactly the same thing, and it's not got a round eye. It's not changing its focus. It's not shifting its direction. It's pointing at a single point and waiting.
Well, that would mean the Earth would have to be round, and in your example you're given, that's the only option. But if there's two options with the same result, then
But that's the point, though, isn't it? Your camera is doing that. That's what it is measured to do. You can do it yourself.
Isn't this just the nature of looking in a sphere, Professor?
Pardon?
Even in the situation of the camera, the light being received by the sensor is coming into it radially, right? It's converging upon that sensor, right?
All right, but it's doing so consistently.
Yeah,
it's not sort of like just following a particular path for no particular reason. It's consistently showing you what's directly in front of the camera, taking a photograph every so often, or leaving the film exposed for the entire time. You can see the entire star trail.
I'll let the other gentleman continue. I may have lost sort of the specificity of what you guys are actually referring to as far as the observation is concerned.
Well, I'm referring to the fact that as you look at the stars, if you find the point that they're rotating around and point a camera at it, the star trail that you get is always circular. Now, geometrically, if you move away from that point of focus to a different one, some miles away, some lots of miles away, they should not be doing that. Because now you're looking at it slightly more obliquely. The circles shouldn't be circles, they should become more and more elliptical. But what's happening is the entire star field is tilting as you move. We know this because when it's on the equator, they go up and over and under it. They haven't what hasn't happened is that as you move away from your pole, everything's just got lower and lower and lower and lower and lower until you've got a blank sky above it, and all the stars kind of compressed below it, which is what you'd expect to see if.
Well, it depends on which direction you're looking as well, Professor. Because if you're looking due west and you're on the equator, look, you'll see two rotating star fields, not just one. So it's just such a big heaven above us, right? That it just goes off in the distance. That tilt is an illusion of your latitude. If you go to 90, right, it's going to be right above you. You know that, I guess.
Right at all.
And then as you
Am I-
go
am
away
I
from
muted?
it south.
The same point that you
Oh,
were
sorry.
looking at, your North Star,
Hello?
is still the North Star, or near it. The fact that it's now
Okay,
on
I'm
the
muted.
equator, on the horizon, and
No,
everything
I
rotates
can hear you. Just
vertically.
one sec, Professor. Professor, just
Yeah.
1 second. We can't hear you. I'm just gonna, if you don't mind, Professor can finish, and then is that you, Reese? I can't quite
Yeah,
hear the voice coming
it's
through.
trying to be. Yeah, I'm trying to be
Yeah.
Riggs. Yeah.
Just 1 sec, man. Let Professor, if you don't, if you can finish off, and then Reese can jump in. That's cool.
Yeah, no problem.
We're going soon, but all I'm saying is that for the same point that you're looking at, the rest of the sky is a bit of a red herring. It doesn't matter what the other rotation is doing. Your star is on the horizon with stars rising above it and seeming to at least go below it and round it in that plane. It's as if the entire sky has tilted through 90 degrees. And at 45 degrees latitude, it's at 45 degrees, and at 0 degrees latitude, it's pointing right above you. It's like an umbrella, where you're looking down the... if you put an umbrella directly above you, and you hold it out, and then move away from it, that's one effect. If you hold it so that the shaft is sort of a continuation of your arm and sort of like point it away from you, the umbrella is still round in front of you. Well, it's as round as it was. Sometimes they're pointy, but that's neither here nor there. And if you twirl it, if you had some, I don't know, little stickers on it or something, they'd be circular, because you're looking down the shaft straight at the point of focus in the middle, and the things are going around it. If you left it twirling vertically and walked away from it, then the pattern of those little spots becomes increasingly elliptical for all that the umbrella seems to be getting lower and lower. That's the difference between what we expect to see, what would happen on a flat surface, and what would happen on a curved surface. And that's it's a matter of expectation.
That's a bad analogy. It's a bad.
Hey, Riggs, I don't know. I can't hear
All
so much.
right.
I got a lot of background noise. You want to roll, Riggs?
I'm going to put. Is my microphone working? Hello.
It's
Sorry,
it's a little bit poor, but I got a shit situation myself.
Is it bad? Is it bad?
Nah, it's good enough. Hit it.
All right. I'm going to hit it. So I posit that the sky is, it's subject to perspective, and also it is a dynamic sky. So, what you're claiming that we would expect to see on a flat surface actually totally doesn't apply, because in your paradigm, the objects are where you see them because you're looking at them directly. In our paradigm, the sky is dynamic in that there is a much more variability in sky phenomena because you're not directly looking at something. The sky is an apparent phenomena. All of it. Not just the 15 degrees, but the whole thing. All right. So that's the first thing. Number two, I have a falsification for your assumption, which you repeated ad nauseum, which got really hard to listen to because you just kept repeating yourself. A simple falsification for your assumption about the rotation of the stars making the arc in the sky is that whenever we have shooting stars, you never, ever, 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 I'm trying to do as many repetitions as you did, ever see them go directly up from the horizon. Ever.
Same with rain. Raindrops never come directly up.
Not sure why you'd expect raindrops to. Think about the asteroids. You're wrong. They do. They do.
Yeah, Matthew, that's the point because it's come. Hold on, Matthew. That's. Oh, sorry, man, Matthew. That's actually the point that he was making. Is that raindrops always fall? It's because they're falling down. They're always coming down. They're not shooting up.
Yeah, I'm not sure what Matthew was saying, but I was talking to the professor guy. Yeah, so when I talked to I think it was Dr. John, and it was it might have even been Professor Parks, or who's that guy that's here in the morning, the Christian dude that never talks. Anyways, I've addressed this with a few different people, and yeah, Danny Faulkner. I've addressed this with many different people, and whenever it comes to the shooting stars or sky phenomena in general, it's always as if it's going at an angle or in a circle-ish around what would be like a flat surface of an Earth. You never see any kind of phenomena that's shooting upward from the horizon as if it's coming from behind the curve, going tangent to that side of the Earth. So unless you can like show this phenomena, I don't really see that you have a fair argument, because it's kind of falsified unless you're saying that where you are on the curved Earth is somehow special to phenomena. But then that would be our position. So unless you're a flat earther or something.
Okay, I can say exactly two things about that. Okay, the first is when we're talking about the stars, a discussion of meteors or what have you, meteorites, is kind of a little out there. It's different. It is different anyway. It's a different thing. However, I would dispute that was never seen. Now, I'm not an astronomer, as I've said. I'm a historian, not a physicist. Okay, but I would consider that to be extraordinarily unlikely. But I would also expect to see that would be something that we could maybe go and find out about. It's the sort of thing which I would think, well, okay, that seems an interesting observation. Let's see whether that really ever does happen. And
yeah, well, it should be just as common as all the other phenomena, but it just isn't.
It depends, in a sense. It depends why, if you're not seeing it as much, is there a reason for that or isn't there? Now, I understand why you're saying what you're saying, okay? And it seems a perfectly reasonable question, a good question. And I don't know the answer to it. Because I don't know the answer to it, I can't really tell you, no, I think you're silly because, or, oh my goodness, you're right because. So I'll have to kind of defer on that one and come back another time.
There actually aren't any answers for it, just so you know. There really aren't any.
You find that it's just a question of where you look.
No, I'm saying for like the heliocentric globe explanation, like there aren't any for why. Because yeah, shooting stars should equally, like if we were on a globe, like the shooting stars would equally be darting in all different directions, down near the horizon, coming up to the left, to the right, to the up, down. Because if you were on a globe and they're, out there in space, and you would see them from all directions. However, if you're on a planar surface with the sky above, those, whatever they are, those streaks in the sky would actually be more local to you, with your local area, and they would never be shooting up from the horizon, because obviously not being on a globe to where there's like space down below the Earth, there wouldn't be anything shooting that way. So you would only see them streaking across the sky. And once you get all the way down near the horizon, like even if you do see one, it's never going to be streaking up like it would if it was a globe. You would still see it moving, either coming, in one direction or another, but never actually coming from, like the terminator point of where the globe Earth would be intersecting with the rest of space. You never see that intersection point, shooting stars moving in all directions at that point. You only see them streaking across the sky above the surface.
I have a geometrical answer to that. Would anyone like to hear it and see my diagram on my screen share?
Please.
Okay. Point in time, or even just where the Earth is around the sun. It may be that as the Earth takes its 365 and a quarter day journey around the sun, that it part of that
speculation
brings it to a place where there's just a lot more junk flying around.
The standard mainstream answer to that is that sometimes we fly through the path of where certain comets have gone, and we know that there's typically a lot of debris in those spots. So
Stardust.
Yeah.
And what you call those spots Virgo, and you call those spots Gemini, and yada yada yada.
They're typically named after the constellation that they're in. Like the Perseids are generally emanating from that constellation. Perseus.
It's coming from the constellation, or it's coming from the position inside of the solar system?
It's in our orbit.
Oh, it's coming.
I would almost agree
from the solar system, but in that direction. Sorry, go ahead.
Man, I would almost agree with this. There's one little stipulation I guess I would hold as a flat earther, or the way I view the above worlds, and things of that nature, luminescence or luminaries, I just look at them as living plasma. But so, have we ever had a meteor shower that could prove a ball like where meteors are falling straight down from, let's say, Chicago or Canada, and then at the same time from New Zealand or Antarctica going down, and both of them going down? Then I would start thinking, differently. But unless our realm is just that spread out where both could see it, the northern and southern hemisphere, I just don't see it that way, though. Anyway, go ahead. Thank you for showing this.
Hey, Jesse, how high up is that blue line above the surface?
70 miles.
So wouldn't we have, if they travel an average of 100 miles through the atmosphere, and that's like at an angular, what if they come almost flush like a 90-degree? Wouldn't we, which they should be all the time, shouldn't there be, meteorites all over the place, impacts happening all the time? If it takes longer for the meteorite to burn up than the amount of atmosphere that it has.
I think the 100 miles was the maximum that they can do at a glancing angle in that thin atmosphere up there. Coming straight down, getting into the massively denser air, then they wouldn't be able to go as far. But the question was,
do you think that's the electric field when it comes down through it and it's just ionizing the gas? It's like because the type of metal is an electrical arc instead of like a cold colored piece of ice.
I'm not sure I follow that exactly.
I'll answer that. I think that the streak caused by meteorites are the metals in the meteorite vaporizing and turning into hot gas. So it doesn't have to do specifically with electricity, but they're bright because it's like superheated metals.
Yeah, and a good example is hydrogen mixed with boron, and then have a tungsten rod. I don't know if you know what those are, but they're pretty badass. But you mix hydrogen, boron, and it has a chemical reaction, and it's such a high energy it burns at 3,800 Fahrenheit. But they're short lived. But they can do these in vacuums, and not even vacuums. As long as there's a place that enough gas can be ionized and burnt that fast, I think the metallic properties of some metals coming through the atmosphere, I would think it would cause electrical arcs, like such hot, really really hot temperatures.
Yeah. Why do you think we don't hear sonic booms when these things enter the atmosphere going so fast?
Going to roll the sky open. It's going to roll itself open, and the stars are going to fall to heaven. So, what does that tell you about the size of the stars? They're pretty small as well.
Okay. The other thing that I was going to say has just gone completely out of my head. I'll have to.
Sorry, Jesse. Or Roger. Sorry, man.
That's all right. No worries. It's
All
not
the
your
things you
fault.
said, all the things you said, running through my head.
The wind was in my mind. I'll be back in a sec.
So Jesse, how high up is the first level of the firmament?
I beg your pardon?
How far up is the first layer of the firmament? You know, it's kind of like a force field, like a crystalline, kind of plasmatic, kind of alive, like a kind of like the cornea of our eye, sort of like that.
Well, what's the context?
Like a membrane. Oh, just you know, about these damn meteors falling, and could it be coming from the firmament, like pieces breaking off? If you know, if it's prophecy that that's what happens.
Jesse and I don't think. Just to be clear, Jesse and I don't think that there are pieces of the firmament falling off that cause meteorites.
Yeah.
Okay. No problem.
I've not been.
They're both globers.
Yeah.
I've remembered.
I've not been convinced of flat Earth just yet, but my mind's still open, and everyone is welcome to try to convince me.
I remember the point that I was.
I bet I could. Go ahead.
Just very briefly.
I've not been.
They're both globers.
Yeah.
I've remembered.
I've not been convinced of flat Earth just yet, but my mind's still open, and everyone is welcome to try to convince me.
You know, if it's prophecy that that's what happens, and
Jesse
we just
and I
see
don't
pieces.
think. Just to be clear, Jesse and I don't think that there are pieces of the firmament falling off that cause meteorites.
Yeah.
Okay. No problem.
I've not been.
They're both globers.
Yeah.
I've remembered.
I've not been convinced of flat Earth just yet, but my mind's still open, and everyone is welcome to try to convince me. I've not been.
They're both globers.
Yeah.
I've remembered.
I've not been convinced of flat Earth just yet, but my mind's still open, and everyone is welcome to try to. I've not been.
They're both globers.
Yeah.
I've remembered.
I've not been convinced of flat Earth just yet, but
Falling off that cause meteorites.
yeah.
Okay. No problem.
I've not been.
They're both globers.
Yeah.
I've remembered.
I've not been convinced of flat Earth just yet, but my mind's still open, and everyone is welcome to try to convince me.